Hello everyone, welcome back to the video lectures on image and speech processing. So we have been talking about the image compression models. So we will continue and look into the different other compression model techniques that are existing, right? So in today's class we will talk about RLC, bitplane coding and block transform, right? We have looked upon Huffman coding, Shannon-Fanon coding, arithmetic coding, and as well as LZW coding technique in our previous video lectures, right? So in today's class, we will be talking about RLC, bitplane coding, and block transform, right? So what actually is RLC? It is the run length coding, right? So it works on the repetitive nature of the image. So we have the intensities that are repetitive in the image. Then such coding technique, RLC coding, is more advantageous, right? What does it do? It tries to identify the length of the pixel values and encode the image in the form of a run, right? So it works if we have an image, then it works on every row as it is, and it'll try to identify the length of the pixel values and encode it in the form of a run. Okay, each row is written as a sequence, right? So it can, when we are trying to compress, we will access our image in the form of row wise, so that each row is written as a sequence, and that is based on the length of the pixel values. Okay, now what is the length? Length is represented as the run of black and white pixels. So I'm talking about run of black and white pixels. So it means that it is more advantageous for binary image, right? So it is more advantageous for binary image. Since binary images have 0 or 1, RLC coding is important. RLC coding can be used for binary images. So image compression can be achieved, right? It is an effective way of compressing an image. For image, it is also binary image, right? So if we have gray image and binary image, for binary image we will try to use RLC coding to achieve the image compression. These further compression can be done using variable length to code length. Like after doing image compression, we will have a set of sequence. We will have a sequence, okay, that using Huffman coding, Shannon-Fanon coding, LZW coding for reducing the spatial redundancy, whereas we can use Huffman coding to reduce to the variable length coding technique, so that we can have greater redundancy and achieve compression ratio better, right? Where is this used? It is used in CCT standard, okay, to encode gray and binary, and most importantly, it is used in binary images. Okay, what is the CCIT combination? It is for TIFF compression. So we see that we have an image which is having the extension of JPEG, right? We have .png or we also have .tiff, right? So when an image is having an extension of TIFF, RLC coding technique, using RLC coding technique, image compression was achieved, right? So before going to example, we will see what are the steps, how do we do our run length coding. So what is the first step? We have to find the run length vector. So what is this run length vector? What is a run length vector means? We will represent the number of zeros and ones in each row by this form. What is that form? We use intensity value, that means whether it is 0 or 1, and the number of same intensity values in the rows. Okay, so what does that mean? We will see an example here. We have a 3x3 image, right? If you observe here, it is a binary image which is having 0 or 1, right? If you observe here, the first row has 2 ones and 1 0. Then we have 3 zeros and 3 ones. So what do? We write our run length as first row can be represented by intensity value, which is 1, by the number of the intensity values in that row, right? So we have 2 ones here in the first row and 0 is of 1, right? The second row, how do we write? We write it in the form of 0, 3. So there are 0, 3 values. Then how do we write this as 1? We have intensity value. How many number? So 3. So we rewrite it in this form. So this is called as the run length, right? Next, after calculating the run lengths, after writing down the run lengths, what do? We calculate the number of run length vectors. Okay, instead of calling them as run length, we are calling them as run length vectors, right? Run length vectors. Let for an image we have n number of run length vectors. So what do? Now we have to calculate the number of bits that are required to represent the vectors. So based on that, whether we can decide whether an image was compressed or not. So for that, we will try to calculate the number of bits. So calculating the number of bits, so how do we calculate it? We first calculate the number of bits required to represent the vector, right? So first step, before going for calculating the number of bits that are required for image, we will calculate the number of bits that are required to represent the vector. So how do we calculate the number of bits that are required to represent the vector? First, we will calculate what is the length of the vector. So what is the maximum length of the vector means how many pixels? How many pixels are there, right? So in our previous example here, we have written third row is 1, 3. So this 3, whatever we are saying, it is called as the run length. Okay, that is called as the run length. So first we will calculate what is the run length. Then let it be L. Okay, then the number of bits that are required to represent L be B bits, right? So for example, if our run length is 3, so how many bits that are required to represent? We require 2 bits, right? So we can represent it by 1, 1. So to represent L length, we are saying that we require B bits. Then the number of bits that are required to represent the intensity value, let it be B1 bits. Here, if we are considering binary image, then it is either 0 or 1. So it will be only 1 bit. If we are considering for gray image, which can be used for RLC, can be also used for gray images. So based on the intensity value, we have to decide how many bits are required to represent the intensity value. So for that, we are representing it as B1. Then the number of bits that are required to represent each vector. So how do we write it as? We write it in the form as B plus B1. Right? So B is the number of bits that are required to represent the length, and the B1 is the number of bits that are required to represent the intensity value. Then the number of bits that are required to represent the whole image, how do we write? We have n number of vectors, n number of run length vectors. So n into B plus B1. So this will give you the number of bits that are required to represent all the vectors of the image. In short, to represent the image, we require the whole image we want to represent, means we require n into B plus B1 number of bits. Right? So for that, we will see a small example. Okay, here we are considering an image of 3 cross 3 as shown here. Right? If you observe here, we are trying to apply the run length coding. So if we observe here, well, the first steps, how do we do the run length coding technique? First step is we have to write down the vectors. So how do we write the vectors? What are the intensity values that are existing, and how many number of pixels are having the same intensity values. So we'll go by row. So the first row we have 5 zeros. So I write it as 0, which is the intensity value, comma, the number of pixels that are having the intensity value 0. Right? Second row we get it as 0. How many zeros are there? We have 3, and the other vector is, we have the intensity values 1. So how many pixels are having? 2. Right? So what was the third row? So we can write it as 1, which is having 5, and 4th row 1 5, 5th row is 1 5, right? So we have the number of vectors to be 0, 5, 0, 3, 1, 2, 1, 5, 1, 5, 1, 5. So how many vectors do we have? That we are representing it by small n, right? So what is the small n value? 1, 2, 3, 4, 5, 6, right? So we have 6 vectors, 6 run length vectors. We have 6 run length vectors. Now, how we have to calculate now the number of bits that are required to represent our image. So for that, we have to calculate the number of bits that are required to represent each vector. So we have 0, 5, right? We have 0, 5, 0, 3, 1, 2, 1, 5, 1, 5, 1, 5. So these are the vectors that we are having, right? So these are the vectors. So if you observe here, what is the maximum length vector? It is the 5 value. We have 5, 3, 2, right? So what is the maximum value? 5. So run length is, which is L, it is written by 5, right? So to represent 5, how many bits are required? That we are representing it by small b. So how many bits do we require? Require 3 bits, right? So we require 3 bits to represent the value 5. Now we have to find out the number of bits that are required to represent the intensity value, that we are representing it by b1, right? So this is, b is the vector length number of bits, b1 is the intensity value number of bits. So b1 we have here as the values are either 0 or 1. So how many bits do we require to represent 0 or 1? We require only 1 bit. So that it is the 1 bit, right? So what is the total number of bits that are required to represent the vector is 3 plus 1, which is equal to 4, right? So now how many vectors do we have? We have 6 vectors, and we have each vector requires 4 bits, right? So to represent the whole image, we require n into b plus b1, right? So that we have got it as 4 into 6. So that is 6 into 4. So we have 24 bits, right? So if an image of this sort is there, for example, then we require, using RLC coding, we require 24 number of bits to represent. Okay. So if we are not using RLC coding, we have 5 cross 5 as the image. 5 cross 5 as the image. So what are the without RLC? We are talking about without RLC. If we are talking about without RLC, then we have total number of pixels are 5 cross 5, which is equal to 25 bits, right? Now each intensity value is either 0 or 1. So how many bits do we require to represent the intensity value? It is 1. So the total number of bits that are required to represent the image without RLC is 25 bits. So if you observe here, if we are using RLC, we are using 24 bits. So without RLC, we are using 25 bits. So we observe that only 1 bit is compressed, but that is for 5 cross 5. Similarly, if you go for higher order images, then the compression number of pixels that are used for RLC reduces drastically. So when we are using binary images of this sort, where the values are repetitive in nature, then we can go for RLC coding, right? After doing this vectors transform using Huffman coding or LW coding, we can further compress the image number of bits from 24 to further less. So further image compression is also achieved when we are using for RLC. But when we use the other compression models, then it is like fixed. Once the coding process is completed, no other compression can be applied. So we achieve more compression. Whereas when we use for RLC, it is achieved, right? Right. Let's consider another example of 5 cross 5. So let's go through the steps again. So if you are drawing the first row, what is the number of vectors? What are the vectors? We have 0. How many are there? It is 1 only. Usually, if we are counting the number of zeros in the intensity in the first row, we can write it as 0, 3, right? We will count the number of zeros as 3. But if we write it as 0, 3, then it is implied that the zeros are continuous, right? So this will deviating, or it is not as the correct image value, right? For that reason, we have to write it in this form. So how do we write it as 0? 1 is there, only one value. Then 1 intensity values, we have 2 bits, 2 pixels. Then again we have 0, which is of 2, right? Next, second row, how do we write this as 0, 1, 1, 1, 0, 1, and 1, 2. So let me just erase this. Then 1, 0, 0, 2, 1, 2. Then we have 1, 5, 1, 5. Then the last row is 1, 2, 0, 1, 1 as 2. Right? So this is our run length or vectors, run length vectors for this example. So what is the maximum length that we have? We have as 5. So how many bits that are required to represent 3? So we have 0 or 1. So what will that one be? How many pixels do we require? We require 1. So to represent each vector, we require 4 bits. We require 4 bits. Now, how many vectors do we have in value? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we have 14 vectors, right? So we have 14 vectors. Now, if I want to represent it by RLC coding, so how many bits do I require now? I require total bits as 14 into 4, which is around 56. Which is 56 bits, right? So the same image, if I am trying to do RLC coding, I'll represent it using 56 bits. Without RLC, if I'm checking out without RLC, I have 5 cross 5, which is equal to 25 pixels, right? Each pixel value is either 0 or 1. So how many bits, total bits that I require without RLC is equal to 25 into 1, which is equal to 25 bits, right? So if in this example we see that if RLC is used, RLC run length coding technique is used, we require 56 bits. Whereas without RLC, just we try to do our same image, then that is of 26. So image compression is not achieved, right? So from this we can see that the run length coding cannot be applied everywhere. So what is the drawback here is, if the images or if the pixel values are not repetitive, not that repetitive in the image. If you observe here, we see that 0 is there, here 1 is there, 1, right, 0. They are having the value, in each row we have the multiple values, but they are not consecutive repetitive. So when such things happen, then RLC will give you more number of bits. So that is the drawback of RLC. So RLC can be used when we have repetitive nature of the image, right? So when we go for RLC, we will, it is like, we use when we have repetitive in nature. So one other technique, it is the bit plane coding. So what is this bit plane coding means? The run length coding is extended for the multiple level images. Okay, bit plane coding splits a multi-level image into series of bit level image. It is a bit stream truncation ability. So that is the effective approach to provide bit stream, right? So if we have m-bit gray level image, so previously we have seen it for a binary image. Now if we have a gray image, so how do we do it? How do we do the coding is we use the bit plane coding technique. So if we have an m-bit gray level image, then every intensity value can be represented in this form, right? So it can be represented by this form where am minus 1, so on, a naught are either 0 or 1, right? Now each mth order plane is generated by collecting mth bit from each pixel. So what does that mean is 0th order plane has all the 0 bits of the intensity value. So what does that mean is, if I have say 1, 2, 3, so on and so forth, then what do I do as, I represent this, and I'm saying that the image is represented by 3 bits. So how do I write my 1 as 0, 0, 1, right? So how do I write my 2 as 0, 1, 0, 3 as 0, 1, 1. So what am I doing? I'm considering all my 0th order plane. Then I'm taking all my 0th bits of that image. So that is 0th bit of my pixel intensity values. That is 1, 0, 1. So I write it as 1, 0, 1. So on and so forth. I do it for my rest of my intensity values. So these is called as the 0th order bit plane. So this is my 0th order bit plane. So that is how my bit plane coding is done. So after we get this is a single binary image. We can consider it as a single binary image which is having either zeros or 1. So for each matrix we can apply the run length coding. Now let's see this example. We will apply the bit plane coding. So what is that? We have 266677124. So what is this? How many bits do we require? Since it is not specified how many bits we have to represent, whether it is a 3-bit or 4-bit or 5-bit, in the question it is not specified. So when we can take 7 is the maximum value. So how many bits do we require to represent the value 7? We require 3 bits. So what do we write? We can write it as 0, 1, 0, 6 as 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, this is 1, 1, 0, 0, 1, 0, 1, 0, right? So this is the 3-bit representation of the gray level, right? Now what am I saying? I can generate 3 matrices now. 3 matrices, which is the MSB bit plane or the second value bit plane. Then we have the middle bit plane and the LSB bit plane, right? So we have 3 bit planes here. So if I am considering the MSB bit plane, so we will consider all the MSB bit values, right? So that is 0, 1, 1, 1, 1, 1, 0, 0, 1, right? So this is MSB bit plane. This is MSB bit plane. Then we have the middle bit plane. So we are considering the middle values 1, 1, 1, 1, 1, 1, 0, 1, 0. So this is middle. Then we have LSB. So how do we write the LSB bits? 0, 0, 0, 0, 1, 1, 1, 0, 0. So this is the LSB. This is middle, this is LSB, and this is the MSB bit plane. So each bit planes Now we can apply the RLC coding by counting the number of vectors that are existing here, and we can try to calculate the total number of bits that are required to represent our image. So that is how we apply for a bit plane coding technique. So next we will talk about the block transform coding. So in block transform, what do we do is we will construct a n cross n sub image. Say suppose what do we do is we divide an image into small non-overlapping blocks of equal size that process the blocks independently using 2D transforms. So we have an image of m cross m. We will construct a n cross n sub image. Okay, so we will divide this image into many sub images, okay, of size n cross n. Then we perform the forward transform. What is this forward transform? The 2D transforms. How many transforms we have dealt with? We have dealt with DCT. We have talked about DFT. Then we have talked about wash, Hadamard. Then we talked about HAR. Right? So many 2D transforms exist in the image processing. So after dividing this image into sub images, each sub image using 2D transforms, any of these 2D transforms, we can convert the and say apply the forward transfer, and we can convert into the spatial to frequency domain. Right? So after this we get the frequency domain. After we get the frequency domain filter, we are going for quantization. So this transformed coefficient values are quantized and coded. Okay, so that is it. What are the symbol encoder things we have seen, right? So this can be Huffman coding, Shannon coding, it can be LZW coding, it can be RLC, or it can be bit plane, or it can be arithmetic coding. So all these are called as the symbol encoders. So all these are called as the symbol encoders. So after doing that, we are getting a compressed image, right? If we want to decompress the image, so what do? We will try to take the compressed image, do the symbol decoder, right? So we will try to use the reverse of the symbol encoder. We will try to use the inverse transform of the forward transform, right? And we will merge all this. We will merge all the sub images and we get the decompressed image, right? If we observe clearly, if an image is quantized, right? So in the decompression block, we don't have any dequantizer. So that means that if an image is being quantized, then it should be done properly, or it should be done efficiently, so that we are not having loss of image values, right? So that is how a block transform is doing. So when we are using this forward transform, this conversion, how this image compression is achieved is that the small magnitude coefficient values are coarsely quantized. Okay, they are coarsely quantized with little image distortion. Right, small magnitude values are either quantized very minutely or they are neglected. So based on this magnitude coefficient values of the transfer value, we will get the compressed image, right? So this is how the block transform is done. The symbol encoder can be Huffman, Shannon, or RLC, or bit plane coding. It can be any other coding, any encoders. So this encoder is decided based on our application and how much error it can be accepted. So based on that, how much compression ratio, how much redundancy is required. So based on that, we will choose the encoder. So what is the forward? How do we choose the forward transfer? It is also dependent upon our application, but mostly we will go for DCT because the coefficient values are differing from each other, and as well as we can differentiate between the small magnitude coefficient values and the high value coefficient values. So it is when we are going for quantizer, we can use we can either neglect them or we can quantize it. So a compression technique can be compressed image can be achieved properly. So what kind of a quantizer do we use? We use differential pulse code technique, Okay, so we use DPCM because it has a more advantages than the other coding techniques, right? So this quantizer we use for DPCM. Symbol encoder, we can use any of the symbol encoder techniques which we have learned previously, and we use the forward transform, it is DCT, right? So that is, so this Gonzalez book is the image processing, which is the reference that we are looking into. So using that you get more number of information as well as your problems. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.